Hey everybody, this is Phil, and I just wanted to give you an update on my personal project, Fil-C. What is Fil-C? Fil-C is a memory-safe version of C and now also C++. And I just wanted to show you some of the new things that I've been able to get it to do. So here I am in my working directory for Fil-C on my Mac. The first platform that I got Fil-C to work on is Mac on Apple Silicon. So here's the PISFix, which is the place where I install all of these memory-safe programs. One of the programs that I have is an SSH client, and so I'm going to use that to log into my FreeBSD box that I have on AWS. So here it's a memory-safe SSH client running on top of a memory-safe OpenSSL, on top of a memory-safe libc, uh, connecting to just a normal SSH server running on this FreeBSD box. But I've also ported Fil-C to FreeBSD. This is FreeBSD running on x86-64. And so I've got a PISFix here as well. And one of the things that I have is the SSH server. So let's start a memory-safe SSH server on this x86 box. So we start it by doing this, and then it wants to be started from an absolute path, hence my use of $pwd sshd, and I'm going to fire it up on port 10022 to keep it out of the way of the normal sshd that's running on this FreeBSD box. So there it is. It's forked into the background, ready to accept connections. So let's connect back, but this time we're going to use an end-to-end memory-safe SSH connection. So it's a memory-safe SSH client compiled with Fil-C, connecting to a memory-safe SSH server compiled with Fil-C, the client running on ARM64, the server running on x86-64. So it's taking its sweet time, but here you go, it's connecting. And one of the things that I'm pretty proud of that I just got working recently is I've got enough libc support for all the various syscalls and whatnot that I can actually do X11 tunneling. So this is going to be just a normal Emacs. The Emacs itself is not memory safe, but it's going to open on my Mac in my Xquartz X server. But the tunnel is going to be a memory-safe SSH server and a memory-safe SSH client. So the server is going to have to do all the things that you do for tunneling on the server. The client's going to have to do things like open the Unix domain socket to Xquartz and all of that. And all of those things are going to be memory-safe down to the syscall layer. The delay that you see in opening the Emacs is not even because of Fil-C's performance. It's just it just so happens that X11 tunneling between me and AWS has this kind of a little bit of lag. I'm just going to make the font a little bit larger. You can see that once I'm connected, it works fast enough that it's like totally usable. I'm just going to make the font bigger. So here it's Emacs with the font a little bit bigger. And now I'm just going to show you a little demo of Fil-C++. And I'm going to compile this demo on my FreeBSD box, and I'm going to write the code live for you here in this Emacs instance that's tunneling over the memory-safe SSH. So we're living on top of Fil-C right now in the sense that Fil-C is giving us this tunnel, and I'm going to show you just a demo of what you can do with Fil-C, with Fil-C++. So I'm going to include a bunch of C++ libraries. And you can see like the keystrokes are coming through just fine. There's no latency. Fil-C is fast enough that you can do that sort of thing. So what are we going to do? Let's add some things to this buffer. Count equals 100 and o string stream buff, and and let's do hello equals count, and then stuff.pushback buff.stir, and then, oh, I don't know, let's get a string reference into index 42 in this buffer, and then let's print it out. So stir equals stir endl. So let's compile that with not pisfix, build bin playing ++. So this is my Fil-C++ compiler. Vector fun.cpp. And currently Fil-C++ doesn't support exceptions yet, so you have to compile with no exceptions. Let's see what happens when we run this program. No problem, it prints that out. But now let's look at some ways that we can trigger some memory safety violations. So first of all, if I remember right, Vector does not do bounds checking for you, but Fil-C is going to do bounds checking. So let's see what happens here with this modified program that is now going out of bounds of this buffer. And look at that. Fil-C has caught a memory safety violation. The violation happens when we actually try to access this string, because this string reference is pointing out of bounds of the buffer. And so on line 20, let's go to line 20. There's line 20. When we try to print this string, we get this violation, and we even get a stack trace of exactly where the violation happens inside of the C++ standard library. So this is libc++ compiled with Fil-C. Let me just show you what that looks like. Programs, LLVM project, deluge, pisfix, lib. You can see these are all the various libraries that I've compiled with Fil-C, including libc++ and libc++ ABI, which are both compiled with Fil-C++. So hence why we're able to get these kinds of errors from the C++ standard library, because the C++ standard library is actually being compiled with Fil-C++, not normal C++. So let's revert that change. Let's make it correct again. So compile, make sure it still runs. And then I want to show you a fun case of use after free that Fil-C catches. So I'm going to show you a memory safety error that has often haunted me when using C++. So we're going to do this again. I'm going to add more stuff to this buffer. Yikes equals count for whatever stuff, push back, buff, stir. Now, what's going to happen here is this vector has resized when we do this, this loop where we push stuff into it. But the C++ compiler is going to be totally cool with us still having this string reference into what is now a deleted version of the backing store of this stuff vector. So we're going to try to print it here, and let's see what happens. So we're going to compile it again. All right. So you can see that the first one printed just fine, but then the second one gives us a Fil-C safety error, and it's a bounds check violation. The reason why it's failing bounds, and again, it's line 28. Line 28 is right here, so it's when it's trying to print this string reference again. The reason why it's a bounds violation is that after we freed, after the C++ standard library freed the old backing store of the vector, the Fil-C garbage collector has replaced the capability pointer of that string reference with a pointer to the free singleton, which has 0 bounds. So if you try to access anything whose capability has been replaced with the free singleton, you're going to get this bounds violation. Now, it might be that the garbage collector hadn't run. Well, first, before we talk about that, let me just show you that the garbage collector is in fact running. You can see it's running quite a bit. It's a concurrent garbage collector, so the fact that it's running so many times doesn't really matter. But let's inhibit it from running by giving it a large minimum threshold, big number. So in that case, what happens is we still get a safety violation when we try to print the string. But in this case, the garbage collector hadn't yet replaced that capability with the free singleton. So we're just getting the free capability in place. When this vector buffer gets freed, the buffer's capability gets replaced with this free thing where all of the types are marked free, and then you can no longer access that memory and you get a safety error. So regardless of whether the garbage collector runs, Fil-C will catch this error. The only way you can tell whether the garbage collector ran is whether the error is a bounds violation on the free singleton or a type check error on a freed capability. So there you have it. We've used Fil-C's SSH client, a memory safe SSH client, to log into a memory safe SSH daemon. And then we started Emacs over an X11 tunnel that's totally memory safe. And we used that to write some broken C++ code and compile it with Fil-C++ to demonstrate Fil-C++ catching memory safety violations. All right. Thank you for watching my demo and have a great day.